All right, good afternoon, everyone.
Mr. Strong, I need to know the answer to the story now. It's been bugging me all day.
All right. Well, that's kind of where we started, where we're going to start. So, okay. Well, let me take the roll really quick, and then we'll get back to our story. Okay, so, Jimmy.
I'm here.
Joanna.
I'm here.
Ashley.
Here, and also I'll be leaving around 3:30 today for a game.
Okay, thanks. Marissa.
Here.
Jerica. Let's see. What name did you say you went by, Jerica?
She went by Caroline.
Oh, Caroline. How could I forget that? All right.
And it's very sweet.
Caroline. As long as it's not destroyed by a hurricane tomorrow.
True.
Courtney.
Here.
Jada.
Here.
Autumn.
Here.
Matthew.
Here.
Weston.
Here.
Chan.
Here.
Kelly.
Here.
Let's see. Seth.
Here.
And Trey.
Here.
Kayla.
Here.
Tobias.
Here.
Nathan.
I'm here.
And Rebecca.
Here.
All right. Awesome.
Hey, Mr. Strong.
Yeah.
Boo and I will also be leaving at the end of class. We don't know what time yet. We're gonna try to stay as long as possible, but we have a home game, so we're just trying to stay as long as possible. So we don't know when we'll be leaving, or even if we will be leaving.
So you're saying that I should wait to reveal the end of the story till the end of class?
No, you should definitely
No.
not do that.
No.
All right. Well, I thought maybe you didn't want to miss the calculus, but it was okay to miss the story or something, right? But no. No, we're going to start with the theorem. So, yeah, I do appreciate it when you guys give me the heads up, either email or whatever, when you let me know what you're leaving. And I know a couple of you have done that already, and I do appreciate that. Now, I am going to try to get a little quicker turnaround once I start getting back into my regular office hours. Hopefully I'll get better, putting the videos up quicker as they get posted. Usually they get posted within a day or two, and so I need to get on that too and get the videos of class so that if you do have to miss for athletics or whatever, like we talked about, is if you watch the class video and then let me know that, then I'll give you those attendance points or whatever. So, okay. All right. So any other questions or concerns before we get started here today with our story?
What time does the test close tomorrow?
Okay, they're typically supposed to close at midnight, and I think that there was one. Was that this class that somebody emailed me and said that they got home from work, and anyway they were going to take a test and it closed early. Anyway, that was a mistake if it closes. So typically I have them close at midnight. Okay. All right. Anything else? Okay. So you remember where we were in the story? So the about Sherazade, she's telling these stories to keep herself alive, There's actually, if any of you are into music, there's actually there was a Broadway musical of Arabian Nights, and there's a song called about Sherazade, and it's written. I can't remember the composer, but it is an absolutely beautiful song. So, like if you like orchestra music or a violin, I heard it played a violin solo, and it was just magnificent. So, if you're interested in that kind of thing, let me know, and I can try to get you some more information on it. So, but okay, so the story that she was telling that relates to the calculus was the one about, so this sister, she loses her brother who's in the clutches of this evil wizard, and the evil wizard turns him into a black grain of rice and then throws him in the desert. And so she goes to the good guy sorcerer who gives her these enchanted platters, and he puts a spell on these that is her path as it goes through the desert. She's to go back and forth between these two platters. But the platters themselves, as they go on, they get slightly closer together. And so then as she goes back and forth, her path becomes less and less. And so at first she's on the horse, but then at some point the platters come closer together. It's just easier for her to get down off the horse and just walk back and forth. And then finally, at the end, she gets down on her hands and knees. And because the platters are, again, closer and closer. And so then as she gets on her hands and knees and starts looking in the sand, she finds it. She finds the black grain of rice that is her cursed brother. Okay. So she is able to take that back to the sorcerer, and he is able to cure the brother. And so then they're able to go off and live happily ever after. I think what Sherazade does then is picks up the story with the tale of this this hermit that's this evil wizard, and kind of follows his story for a while. So I always wondered if like he becomes like Jafar, the bad guy in Aladdin, but I don't know. Anyway, okay, so that's how the story ends. That part ends, is that she's able to save her brother. So what does this have to do with calculus, and why would I take this time? Okay, well, it has to do what's called the sandwich theorem. Okay, now what does the sandwich theorem have to do with the Arabian desert? Anybody know? Well, it's because of all the sandwiches there. Get it? Okay. Anyway, all right. That's a bad joke, but no, it has to do with the idea of two functions. And then we have, let's say if we have another crazy function that we don't know what its limit is, but if we know that it's sandwiched between these two functions, then at some point they come together. And so if that's the point that we're interested in, then we're golden. Okay, so for example, let's suppose we want to find the limit of some function as x approaches infinity. And let's say this function is so complicated that we have no idea how to find its limit. Okay? And so I'm not even going to give you a function. I'm going to just call it limit of f of x. But I mean, let's say it could be like x squared cosecant x over the square root of 1 minus sine squared or something like that. Okay, I don't know. Could be something complicated. But what we're going to say is, suppose that the function that I give you is between negative 1 over x and 1 over x. So it's sandwiched between those two. So then what we do is we think, well, what would be the limit of each of these as x approaches infinity? So we say, well, any constant over infinity, it doesn't matter if that constant's positive or negative, if the denominator's getting bigger, you think like if you have like 1 over 100, 1 over 1,000, 1 over 1,000,000, that number's getting smaller and smaller. And till at some point it approaches 0. Well, it approaches 0 as x gets bigger and bigger. So then what that means is that as x approaches infinity, if this first function approaches 0 and the last function approaches 0, well, the one that's sandwiched in between also has to approach 0. Okay? So it's like this. So the limit of one function approaches 0. The limit of the other function approaches 0. So the one that we're interested in, we don't even know what it is. But if it's sandwiched between these other two, then its limit as x approaches infinity is also 0. Okay? So that's the idea of the sandwich theorem. So typically, when we're given a function that's between two other functions, then the other two functions are the ones you actually take the limit of. Okay? And what you hope is that if the outer two functions give you the same limit, then the one in the middle is that as well. Now, if they give you two different limits, then you can't use it. So most of the time when I give you one that you use the sandwich theorem, they'll give you the same limit. Okay? Any questions on that? Okay, so the sandwich theorem is so called because it refers to a function whose values are sandwiched between two equal limits, whose limit well, actually, I guess the function is sandwiched between two functions. Sorry. I'm just looking at the wording here. The sandwich between two functions that have an equal limit. Okay, the sandwich theorem is also called the squeeze or pinch theorem. Just depends on the book. But it's all, the idea is the same. Okay? So here's your f of x is the blue. So it could be any kind of crazy function. And it's sandwiched between the red and the yellow. So it could be equal to, but has to be between. Okay? So to find the limit as x approaches c, then see, since the red graph has a limit of L and the yellow graph has a limit of L as x approaches C, then the blue graph must also have a limit of L as x approaches C, because it lives between those other two. Okay. So let's say we wanted to know what's the limit of u of x as x approaches 0. Okay. So then the idea is to say, well, actually, here, let me write it up here. So we'll say that 1 minus x squared over 4, that's the yellow one, is less than or equal to u of x, the blue one, is less than or equal to 1 plus x over 2. So if we want to find the limit of this function in the middle, then really what we do is we find the limits of the outside ones. We say, okay, well, what's the limit of the bottom one? 1 minus x squared over 4 as x approaches 0. Well, if we plug in 0 for x, we get 0 over 4, which is 0. 1 minus 0 is 1. And you can actually see that from the graph. It's 1. All right. Then let's look at the limit of the red one. Again, we plug in 0, and we get 0 over 2 is 0. 1 plus 0 is 1. Okay? So, if we want to find the limit of u of x, and I don't even know what that is, then you say, well, since this is between the other two, then that means the limit has to be between the other two. And that means that if the first one's limit is 1 and the last one's limit is 1, then the limit of the function that we want as x approaches 0 has to be 1. Okay? So, when you see one that's set up with the sandwich theorem, typically what you do is you check the limit of the functions on the outside. And if they match, that's your answer. Okay? All right, any questions?
What happens if they don't match?
Then that means that either you've messed up or you can't do it. Okay? You'd have to do it some other way. All right? Okay, so it says use the sandwich theorem to find the limit as x approaches 0 of x squared times the sine of 1 over x. Hence, consider comparing to y equals x squared and y equals negative x squared. Okay, so in this class, I will always give you the functions to compare it to. So the ones on the outside. So we're saying that this function is between these two. Okay? It's not till the end of Calc 2 or Calc 3 where you have to come up with your own functions to compare it to. So I'm telling you to compare it with those two. And then it says if you get stuck, look at the graph. All right, Trey, when you've got it.
Yeah, I'm kind of stuck right now.
Okay, so with this hint, what it's saying is that this function that you're trying to find the limit of lives between these two. Okay? All right? So, Let's see here. So here's y equals x squared. Here's y equals negative x squared. Okay? So what we're saying here is, here, let's move this red one. Whoop. So what we're saying is the function that I give you to find the limit of lives between these two. Okay? See, this one is kind of complicated because if you just try to like plug in 0, then you get the sine of 1 over 0. And how do you do that? How do you take the sine of like infinity? That's kind of hard to even wrap your brain around. Okay? So, but the point of the sandwich theorem is you don't have to deal with the hard one. Just deal with these on the outside. See, what would be the limit of negative x squared as x approaches 0?
0.
And how about the limit of x squared as x approaches 0? Go ahead, say it.
0.
0. Okay? So then the point of the sandwich theorem is that if you can calculate these limits on the outside, then that answer is going to be the limit you're looking for. Doesn't matter how complicated this is, this is how you do it. So the answer that you're looking for is 0. Okay? All right, any questions on that? Okay. All right. So, one application of the sandwich theorem is if a function is less than or equal to another function in an open interval containing c except possibly at x equals c itself, then the limit of both functions as x approaches c, one limit is always going to be less than or equal to another. So, what does that mean exactly? That means that if one function is always less than or equal to another function in the graph, then wherever you take the limit, because remember the limit is the y value. So the limit of anywhere along the red function is going to be less than the limit on the g function. Because this function is below this one. It's less than or equal to. So the limit has to be less than or equal to. Okay? All right. Now, so I'm going to do another example of the sandwich theorem. And this result is actually going to be super important. Okay? And so here we're trying to look at what happens between sine theta. If the sine of theta is between negative absolute value of theta and absolute value of theta. Okay? So if we look at the limit of each of these as theta approaches 0. Okay? Whoops. Okay, so we have the limit of sine theta as theta approaches 0 is 0. Because, see, if by the sandwich theorem, as theta approaches 0, well, the absolute value of 0 is 0. Okay, same thing here. The absolute value of 0 is 0, the negative of 0 is 0. So this one is 0, and this one is 0. So by the sandwich theorem, this part in the middle is 0. So the limit of sine theta as theta approaches 0 is 0. Okay? Well, we probably could have figured that out just from the graph. Because, see, if we look at this blue graph here, See, as sine theta gets closer to 0, as the angle, as theta gets closer to 0, the y value here gets closer to 0. So we probably could have figured this one out. Okay? But now, all right? But see, if I were to take, let's see, I lost my, okay. Huh. Okay, so if I were to take my original problem here and divide it by theta, see, then I'd have the absolute value of the negative absolute value of theta over theta is less than or equal to sine theta over theta is less than or equal to theta over theta. Okay. Well, so theta divided by theta is going to be 1. And if theta is negative, then the absolute value of theta is negative theta, and then a negative of negative theta is positive theta. So this is also going to end up being theta over theta, which is 1. Okay. So again, so if theta is negative, so on the left side of 0, then the absolute value is the opposite of it. But here we're taking the opposite of the opposite, so that will be positive theta over positive theta, which is 1. So then now if we take this limit as theta approaches 0, see, this is 1, this is 1, and so this limit has to be 1. Now, so this limit, the limit of sine theta over theta as theta approaches 0 equals 1, okay, that is going to be the first limit that I ask you to memorize, okay? I want you to memorize that result because it pops up all over the place. And when we're calculating like really hard limits, we actually use that a lot, okay? So it's going to come in handy a lot. So the limit of sine theta over theta as theta approaches 0 equals 1. Now sometimes instead of theta you'll see x or some other variable. So the limit of sine x over x as x approaches 0 is 1. Okay? All right, any questions? All right. Okay, so use the graph to determine what's the limit of cosine theta as x approaches 0. Now, this is a little tricky. This is not an obvious question because this graph is 1 minus cosine theta. Okay? So see if you can use this graph to figure out what's the limit of cosine theta. All right. So Autumn, what do you think?
I'm not sure. I'm kind of lost on this one.
Do you want to take a guess?
Would it be 0?
Okay. See here, the limit of 1 minus cosine theta, this blue graph, is actually sandwiched between these two at 0. Okay. So, because it lives between the green and the red. So, the limit of 1 minus cosine theta as x approaches 0 is 0. That's correct from the graph. Okay? But I didn't ask for the limit of 1 minus cosine theta. I wanted just the limit of cosine theta. So, can anyone use a little logic here to see if you can figure that out? I mean, you can actually use some algebra, but it might be easier to actually reason it in your head.
No.
So what do you think?
Would it just be 1?
It would just be 1. Okay, tell me your logic there.
Well, I believe that 1 minus cosine is the same graph as sine, and so I kind of used the last problem, and I also just added 1, just shifted it over. That was also...
Yeah, see, look. Okay. So this limit is 0, right? So think 1 minus what would be 0? 1 minus 1 would be 0. So this has got to go to 1. Okay? So if we know, if the limit of 1 minus cosine theta is 0, well, I could actually subtract 1 from each side. So this is what I'm talking about, use some algebra here. And then multiply each side by -1. So that would give us the limit of cosine theta equals 1. Now think about that. Don't you know that the cosine graph actually goes through the point 0, 1? So when x approaches 0 from each side, the graph of the cosine goes to 1. Okay? Here, let's this is what I'm talking about here. See, if I were to graph the cosine graph, it actually starts up here at 1. Okay? And so as x approaches 0, the cosine graph is at 1. So that would be the one. All right? Any questions on that? So when you do some of the practice problems, sometimes there'll be little tricky things like that. Okay? You got to be a little bit careful. Okay. All right. So we put this up yesterday. So I just kind of want to remind you that when you're calculating limits, the first thing you try to do is just plug in the number. Okay? If you get a number, great, you're done. Otherwise, if you get 0 over 0, then you got to factor and cancel and plug in again. Okay? Some different tricks that we've learned here are to multiply by the conjugate, especially when you have a radical. And then if it's of the form blob is less than the function is less than or equal to a different blob, okay? So the function is between two weird things, that's the sandwich theorem. And so then that's when you calculate the limits of the two ends, the two sides, and then see if they match. Okay? And then if you get stuck, try using a table or graph in the calculator. Okay? And then the last thing, which is kind of covered up here, says use a previous result. Okay? Math is famous for doing this kind of stuff where you'll do like 10 steps to get the answer for number 5, And then problem 6 will use that result to get the next one. Okay? So believe it or not, sometimes you have to look back on previous problems that you did. Okay? All right. So here's an example of how we're going to use the limit that I asked you to memorize. The limit of sine theta over theta as theta approaches 0 is 1. All right. So suppose I wanted to find the limit as x approaches 0 of 2 sine x over x, 2 sine x cosine x over x. Okay. Well, if you just try to plug in 0, you're going to get 0 over 0. And this doesn't factor. But, see, you can group together the limit of sine x over x as x approaches 0, because it's not like these cancel, but that this limit goes to 0. Okay? And so then your answer would be 2 times 1 times, well, if you plug in 0 here, cosine of 0 is 1. So 2 times 1 times 1, so the answer would be 2. Okay? So remember, like, if you forgot that the cosine of 0 is 1, remember on the unit circle, cosine refers to the x value. So the x is the cosine, the y is the sine. So as we go out 1 unit, we're at 1, 0. So at 0 degrees, the cosine is 1. Okay? Now, okay, this is not, let's see if I can manipulate this from the screen here. Okay. So let's look at another type of this. This is, let's say I needed to find the limit as x approaches 0 of sine 5x over 3x. Okay? Now, in order for it to cancel, I mean, you can have thetas or x's or whatever, sine theta over theta, sine x over x, but these have to match for it to get to 1. Okay? So if they don't, then this is the kind of trick that you do. The algebra trick that you do is you say, okay, I don't need a 3x there. What I need is a 5x. Okay? So actually, I don't need to multiply by the x. I just need a 5. So what I'm going to do, okay, so what I'm going to do is just multiply top and bottom by 5. Okay? So then what I can do is rewrite it and say, okay, now I've got the limit as x approaches 0 of sine 5x times 5 over, and then I'm going to put the 5, I'm going to just reorder everything, commutative property, so 5x times 3. Okay, so now this part right here, sine 5x over 5x, since those match, that'll go to 1. So when I calculate the limit now, I just get 1 times 5/3, and so my answer is 5/3. Okay? So that's why it's very important that you know that sine theta over theta as theta approaches 0 is 1. Okay, because we're going to use that a lot. All right, any questions on that? Okay. All right, so I think that's the end of 2.2. All right, any questions on that? Okay. Okay. All right, the next section is what we call the precise definition of the limit. Okay? So this section, probably more than any other section that we do, would be for anybody that wants to become like a math major, or go into it's a little more abstract, a little more theoretical than most of the sections that we do. But I try to figure out a way to make it a little bit more realistic, or apply it to some everyday things. But this is a very abstract lesson, the precise definition of the limit. Okay, so what we're going to do to start off with is think about the idea of a target. Okay? All right, so like let's say that if we're, shooting a bow and arrow, and we have a target that we're going to call the bullseye. Well, and so whatever that target is, that's what we want, right in the middle. But sort of the radius of the circle, anything in there, we're actually going to say is a bullseye. So the bullseye, the circle in the middle of the target, is actually a little bit bigger than the width of the arrow. So there's a little bit of fluctuation there, a little bit of tolerance, so on. And so what we're going to start off with is think about how far off we can be from a perfect hit, a perfect target. All right, now we're going to use the Greek letter delta for how off we can be and still be in our target range. Okay, so that little d stands for like the difference. Okay, so here's the idea. Suppose that we graph on a number line between 2 and 10. All right, and let's say our target is 5. Well, if the delta is 3, then what that means is that we can be off by 3 in either direction. Now, these arrows here are indicating the acceptable values. They're not to go on forever in each direction. So what this is saying is that we will accept any value between 2 and 8. Okay? It's kind of like if you're working in, let's say that you're in a factory, and you're making something, and the boss tells you you have to make it to this specific dimension. Well, you can be off a little bit, but if you're too far off and it doesn't pass inspection, then that's going to be considered a default, or it'll be rejected. And so then, maybe you don't get paid as much. Okay. So we have our tolerances, like how far we can be off. Okay. So to help show that the limit of a function as x approaches a number is equal to some number L, we can sketch the interval on the x-axis with x sub 0 inside. Then we visually determine the delta. And that's the distance to our target, the point x sub 0. Now, this is how I write the deltas. Some books, some teachers might write it like any of those ways. Okay? But this is the formula that we're going to be using in this section. Okay? And this says that if 0 is less than x minus the target, absolute value is less than delta, then that implies that the function minus the limit's absolute value is less than this little e, which we're going to call epsilon. Okay? Now, I know it's all Greek, but it'll make sense tomorrow as we continue with this. Okay? But you need to write this part down. We're going to use this a lot in this section. Okay? We're
Wait,
also
is that L inside the absolute
this is
value
an L.
and L?
f of x minus L,
And then the other one is less than?
less than epsilon.
Okay.
Okay? Now, tomorrow I'm going to answer the question is how did this idea help Germany lose World War II? So if any of you history buffs, okay, if you know a lot about World War II, we're going to talk about what this actually has to do, how World War II has to do with this. Okay? All right.
Hey, Mr. Strong,
Yes.
can you go back to the previous slide and scroll up really quick? I didn't finish
This
writing
one?
it first. And then, yeah, I
This
just
one?
need to write that down really quick.
Oh, okay, sure.
Thanks.
Okay, go.
Thanks.
Okay. Oh, and remind me to tell you, I'll tell you a German joke tomorrow, if you remind me. Okay, so I don't know if we'll have time to finish this example, but so let's say if we've got 1 minute. So sketch the interval from 2 to 12. So I want you to do practice 0 on your sheet. So what you do is if x of 0 is 7.1, then to find delta, what you do is you measure this distance from 7.1 to 12, and then from 7.1 to 2. And so whichever one's smaller, that's the delta. Okay? So your target then is, if delta is 4.9, then you can be 4.9 off in either direction. So then your acceptable values aren't from 2 to 12, but 2.2 to 12. Because you measure delta in each direction. Okay? So see if you can do that for